So if we got a known mass, the radius of the circle around which it's moving, and its angular velocity, we can figure out its kinetic energy. There's a formula for that, but you don't know what moment of inertia is, so you can't use it. Okay? So and what we're really doing is trying to motivate moment of inertia. Okay? Which allows us to talk about the dynamics of rotating things, rotating objects, extended massive objects. Okay, so from this information we can easily figure out the kinetic energy if we know what we're supposed to know. Okay? Because the angular velocity, the radius, and the definition of a radian allow us to easily work out the velocity along the arc. Okay, in the example we had here, using the estimate that the thing was rotating at 1.5 radians per second, okay? It has a radius of 30 centimeters. Circle 30 centimeters. The reasoning is very simple. In 1 second, the thing rotates through 1.5 radians. Okay, well, every radian is a distance along the arc equal to the radius, so for every radian, you move 30 centimeters along the arc. If in a second you move 1.5 radians along the arc, you've moved 1.5 times the 30 centimeter radius, 45 centimeters, okay? And you've done that in a second, so the thing must be moving 45 centimeters per second. Okay, so you can get the velocity along the arc just from basic principles, not from formulas that you're going to forget and get upside down and get 2 pi's in the wrong place and stuff like that, which is really easy to do when you're dealing with this stuff, which is why we try to develop it from the first principles so you don't get confused. Okay? Because you ain't getting a formula sheet. Okay? I expect things to be done, and, reasonable things from first principles. Okay? Velocity along the arc then and the mass, well, that gives you the kinetic energy, but you got to know what kinetic energy is. At least you got to know it's 1/2 mv squared, but you need to understand where that 1/2 mv squared comes from to really be able to, for example, go into a lab and analyze a system, to engineer a system, to analyze a system, to model a system in a computer, whatever. Okay? So you got the velocity along the arc of mass to give you kinetic energy. Now we could put this into symbols. Okay? So M, R, and omega. And I'll just give this kind of a flow diagram. A flow diagram, arrow diagram, or the relationship diagram. You got M, R, and omega. R and omega give you V. M and V give you kinetic energy. There you got it. Okay? If you know the definitions, you know how R and omega give you V. Very simple reasoning. And then if you know M and V, you know the formula for kinetic energy. Okay? And hopefully you know something a little deeper than just the formula. And of course you have to know that it's change in kinetic energy is equal to the work done by the net force and all that stuff. Okay? Work energy there. Okay, well, that's it. A very simple diagram. Simpler than most. Okay. Now my question is, if we do work W on this system, what's the change and omega. Now, what's a change in your angular velocity? From concepts.